In this video, we're going to start talking about more complex experiments. Single-stage experiments are experiments that are done once. For example, drawing one card from a deck, flipping one coin, rolling one die, picking one marble from a jar, or things like that. These are the types of experiments we saw in earlier probability videos for the course. Multi-stage experiments involve a single-stage experiment being repeated or multiple different single-stage experiments taking place. For example, drawing several cards from a deck, either one after the other or all at the same time, rolling two dice, rolling one die, then flipping a coin, guessing on 4 different multiple-choice exam questions, or other things like that. Now that we're going to be talking about multi-stage experiments, we need to talk about independent and dependent events. We call 2 or more events independent if the occurrence of one event does not affect the probability of the others. We call 2 or more events dependent if the occurrence of one event does affect the probability of the others. Here we have some examples of independent and dependent events. Independent events are things like unrelated single-stage experiments like rolling a die then flipping a coin. When you roll a die, that's not going to affect whether the coin lands on heads or tails. Repeated single-stage experiments where nothing changes. This would be things like flipping a coin multiple times. If you flip a coin once and it lands on heads, that's not going to affect whether you land on heads or tails the second time you flip the coin. Drawing a card from a deck, replacing it, then drawing a second card. So if we take one card out of the deck, we put the card back into the deck, there's 52 cards in the deck again, all of the cards are there again, and when you take out a second card, the probability is not going to change. For anything where you see the key term with replacement, some examples of dependent events are things like drawing a card from a deck, not replacing it, then drawing a second card. So when you take the card out and you don't put it back in, you change the amount of cards in the deck, you change the makeup of the cards in the deck, so the second probability is going to be different. Anything where you see the term without replacement, also drawing 2 or more cards from the deck at the same time. This one is a little bit confusing, but it's fairly similar to drawing one card, not replacing it, and then drawing another card. We will see one example that deals with this type of situation. Now that we've talked about independent and dependent events, we can talk about what conditional probability is. The conditional probability of an event is the probability of that event occurring given that another event has already occurred. We would denote it like this, and the way we would read this is say the probability of B given A has already happened. If A and B are independent, the probability of B given A is just the probability of B, because the probability of A doesn't affect the probability of B, and the probability of A and B both happening would be the probability of A times the probability of B. If A and B are dependent events, the probability of B given event A has already happened is the probability of B and A divided by the probability of B, and the probability of A and B is equal to probability of A times probability of B given A, and I know this seems a little bit weird, but it does get a bit more intuitive when we get into some examples. So we'll look at our first example now. Suppose 60 tickets were entered into a raffle, 3 of which belong to us. 2 tickets will be drawn. A is asking if 1 ticket is drawn, noted, and put back into the raffle, then a second ticket is drawn. Find the probability that both tickets are ours. So this would be an example of something with replacement or independent events. But first we'll define the events we're talking about. We'll let T1 be the event that the first ticket is ours, and we'll let the event T2 be the event that the second ticket is ours. So what we want to find here is first ticket and the second ticket is ours, and this is going to be equal to probability that the first ticket is ours times probability that the second ticket is ours. Probability that the first ticket is ours is going to be 3 out of 60, because we have 60 tickets in the raffle and 3 of them are ours. The probability that the second ticket will also be ours is again going to be 3 out of 60. This is because after we took the first ticket out, it was placed back in, so there's still 3 of our tickets in the raffle, and there's still 60 tickets total because we didn't permanently remove any. So we multiply this, we end up getting 9 out of 3,600, which is okay. If you want to, you could reduce this to 1 out of 400. In part B, we're told one ticket is drawn, not put back, and then a second ticket is drawn. So because we've taken a ticket out and we're not putting it back in, this is a without replacement problem, or an example of dependent events. So again, here we're looking for the probability that the first ticket is ours and the second ticket is ours. So this is the probability that the first ticket is ours multiplied by the probability that the second ticket is ours, given we already got one of our own tickets the first time. So the probability of the first ticket being ours is going to be 3 out of 60 again. We still have 60 tickets in the raffle to start with. 3 of our tickets are still there at the very beginning. But now we've taken one ticket out, we're not putting it back in. So when we go to get the second ticket out of the raffle, there's only 59 tickets in the raffle total, and only 2 of the tickets in the raffle are ours because one of them has already been removed. So 2 out of 59 is the probability that the second ticket is ours, given we already got one of our tickets out the first time. So we multiply these two together, and we would end up getting 6 out of 3,540, which you could also reduce to 1 out of 590. Now let's look at another example. Here we're told 3 cards are randomly drawn from a standard deck. Find the probability that all 3 cards are kings if the cards are drawn A without replacement, then B with replacement. Here I would suggest pausing the video, try to work this out on your own, then hit play to see me go through the solutions. In part A, we're told the cards are drawn without replacement. This lets us know this is an example of dependent events. So we're looking for the probability that we get 3 kings in a row, and we're drawing the cards without replacement, meaning every time we take a card out of the deck, we leave it out of the deck and we don't put it back in. The probability that the first card we draw as a king will be 4 out of 52. That's because we have 4 kings in the deck and there's 52 cards total in the deck. The probability that the second card we draw is also a king is going to be 3 out of 51 because we've removed 1 king from the deck and we've removed 1 card from the deck. So now we only have 51 cards in the deck instead of 52, and we only have 3 kings in the deck instead of 4. The probability that the third card we draw is a king again is going to be 2 out of 50. Again, because we removed 1 more card from the deck, and because we've removed 1 more king from the deck. And if we multiply all of these out, we end up getting 24 over 132,600, which reduces to 1 over 5,525. In part B, the cards are being drawn with replacement. This means we're dealing with independent events. So every time we draw a card from the deck, we put it back in. So the probability of getting a king the first time will be 4 out of 52. We have 4 kings in the deck out of 52 cards total. We draw a card a second time. The probability of getting a king the second time is still going to be 4 out of 52 because we put the card back. So we put the first card we took out back, so we still have all 4 kings in the deck, and we still have all 52 cards in the deck. Same thing for the third card. Because we put the card back again after the second draw, we still have all 4 kings, still have all 52 cards in the deck. This is equal to 4 out of 52 to the third power, which is 64 out of 140,608, which we could also reduce to 1 out of 2,197. Let's look at another type of example. Here we're being told a jar contains 10 marbles, 2 are red, 3 are blue, 5 are green. If 1 marble is taken out, replaced, and then a second marble is taken out, find the probability that A, both marbles are red, B, the first is red and the second is blue. So because we're being told that the marbles are being replaced, this is an example of independent events. For part A, we want to find the probability that both marbles are red. Probability that the first one is red will be 2 out of 10. We have 2 red marbles out of 10 marbles total. And once we take that red marble out, we're going to put it back in. So there's still 10 marbles in the jar, and there's still 2 red ones. So this will become 4 out of 100, which reduces to 1 out of 25. For B, we're looking for the probability that the first is red and the second one is blue. Probability that the first marble is red is still going to be 2 out of 10. and the probability that the second is blue will be 3 out of 10. Because we replaced the first marble, there's still 10 marbles in the jar, and because we didn't have anything to do with any of the blue marbles, and we put everything back in, there's still 3 blue marbles in the jar. So we multiply these together, we end up getting 6 out of 100, or 3 out of 50. Now we'll look at a version of this problem, except we're dealing with dependent events now. A jar contains 10 marbles, 2 are red, 3 are blue, 5 are green. If one marble is removed, and then a second marble is removed, find the probability that this is an example of dependent events because we weren't told that replacement happens. First, we're looking for the probability that both marbles are red. Probability that the first marble is red will be 2 out of 10. Because we have 10 marbles in the jar and we have 2 red. So that's the probability that our first marble is red. The probability that the second marble is also red will now be 1 out of 9. Because we've removed one of the red marbles. And because we've removed one of the marbles from the jar, so now there's only 9 in the jar instead of 10. So we multiply this out, we end up getting 2 out of 90, or 1 out of 45 as our probability. Now we want to find the probability that the first marble is red and the second marble is blue. The probability that the first marble is red is still going to be 2 out of 10. We have 10 marbles in the jar to start with, 2 of those marbles are red. Now we want to find the probability that the second marble is blue after we've removed 1 red marble. So we removed the 1 red marble, there's only 9 marbles left in the jar, but the amount of blue marbles is not affected. We still have 3 blue marbles in the jar. Removing 1 red marble doesn't change that. So the probability of getting a blue marble after 1 red marble was removed will be 3 out of 9. So when we multiply these, we end up getting 6 out of 90, or 1 out of 15. C is asking us to find the probability that 1 marble is red and 1 marble is blue. Now I know it sounds a lot like what B is asking, but there are actually 2 different situations that could satisfy this. We have the situation where the first is red and the second is blue, or we have the situation where the first is blue and the second is red. These are 2 different things that could happen that would make 1 marble be red and 1 marble be blue. In part B, they want only the first marble is red and only the second marble is blue. So they don't want us to deal with the situation where the first is blue and the second is red. And sometimes if you see problems like this and they tell you, let's say we had this problem and they told us that the 2 marbles were removed from the jar at the same time, they could still ask us this question and we would still solve it the same way. When you get to the homework, there's a couple problems where they ask you stuff like this. I know there's one about video rentals where they give you a problem like this, but they don't say explicitly it's without replacement. That problem is another example of dependent events, and you would solve it the way I'm going to solve this example here. So the probability that the first is red and the second is blue, we know this is still going to be 2 out of 10 times 3 out of 9. And then we would have to add this to the probability that the first is blue and the second is red. So the probability that the first one is blue will be 3 out of 10. The probability that the second marble will be red will now be 2 out of 9. Probability that the first is red is 3 out of 10 because we have 3 red marbles out of 10 marbles total. Then we remove 1 from the jar. There's only 9 left, but the 2 red marbles are still there. So the probability that our second marble is red will still be 2 out of however many marbles are left in the jar. So we end up getting 6 out of 90 plus 6 out of 90, and this is equal to 12 out of 90, or 2 out of 15.